At this stage, we're not going to look at actually integrating the log function. We'll see that in extension 2 integration. But what we're going to look at is going backwards. So yesterday when we differentiated, we got derivative on function. So logically going back the other way, if we want to integrate the situation where we have derivative on function, we must therefore go back to the logarithm. But notice, it's the log of the absolute value of function x, right? Because you can't find the log of a negative number. So log of the absolute value of function x. So 1 on 7 minus 3x, I would like the derivative on the function. The derivative is negative 3. So if I rewrite that, I'll get minus a third the integral of negative 3 on 7 minus 3x. And that will be minus a third log of the absolute value of 7 minus 3x. So a similar sort of one. Derivative of that one would be 8. So I would get an eighth of 8 on 8x plus 5. And we get an eighth the log of the absolute value of 8x plus 5. And this one here. So the derivative would be 6x to the power of 5. So if I multiply the top by 6, and then a 6 out the front, we get a 6. Now notice I didn't bother with absolute values there. And the reason being, x to the power of 6 plus 2, it would be impossible to get a negative number. I mean, you can still put absolute value symbols there, but there's no need to for that one. Okay, so this is an interesting one. 1 on 5x. All right, so the derivative of 5x is 5. I get a fifth out the front to balance it out, and I get a fifth the log the absolute value of 5x. But interestingly, when I do it another way, because remember we can factorise out the integral symbol. So if I write that as a fifth the integral of 1 on x, and then I say, well, hang on, I've got derivative on function, so that's the fifth of the log of the absolute value of x plus a constant. So I've ended up with 2 different answers for the same thing, which of course in maths we don't like, which clearly means that they're actually not different, they are the same. How?
C.
Sorry, what was that?
C is different.
Explain.
C is different. Sorry?
Explain what you mean. Different by how much? Ooh, close. A fifth log 5 it would differ by. See, the first one, you could rewrite a fifth log of 5x as a fifth log of 5 plus a fifth log x. So you still get the fifth log x, but the constants would be different by that factor of a fifth log 5. Integral of 4x plus 1 on 2x plus 1. This one is impossible to create the derivative on top because the derivative would be 2. Well, how do I turn 4x plus 1 into 2? I can't. So before I do that one, if you have this situation, you'll notice we're still dealing with basically polynomials here. But the order of the numerator is greater than or equal to the order of the denominator. Then do a polynomial division first. So this one here, if you don't see it straight away, we could do our polynomial division. So 2x plus 1 into 4x plus 1 goes twice. We end up with a remainder of minus 1. So I can now rewrite that fraction as 2 minus 1 on 2x plus 1. And now we're okay. Because in that fraction, I can create the derivative on top now. I can get that 1 and turn it into 2. And the 2, of course, we can integrate. It'll be 2x. So we'll get 2x minus a half the log of the absolute value of 2x plus 1. Let's do a definite one here. So the denominator is x squared plus 1. Derivative's already there. So I don't have to create the derivative. So I end up with the log of x squared plus 1. And again, notice I didn't have to worry about absolute value there because x squared plus 1 is always going to be positive. Sub in the 2, sub in the 1, and play with our log laws. We get our answer of log 5 on 2. When you are dealing with definite integrals, remember you can't integrate across the asymptote, the discontinuity. This is one of these ones where they first ask us to differentiate something, then go and integrate. So, one would assume when we differentiate, we're going to get x squared log x or some multiple or something plus it. We're expecting to see that there. All right, write down the first diff the second, plus write down the second diff the first, and we get x squared plus 3x squared log x. So there's that x squared log x that we're expecting to see somewhere in our answer. Now go and integrate. Well, we know that when we differentiate x cubed log x, we get x squared plus 3x squared log x. So therefore, logically, if I integrate x squared plus 3x squared log x, I must get x cubed log x, but I've got an absolute value of x, plus a constant. All right, not quite the question they were looking for. We want to integrate x squared log x. So I go back to the left-hand side there. That integral I can split up into two integrals. And I'll move the integral of x squared to the right-hand side. So I've now got three lots of the integral of x squared log x is x cubed log x minus the integral of x squared dx. Well, I can find the integral of x squared dx, but at the same time I'll also divide both sides by 3, and we get our answer. So the integral of x squared log x is a third x cubed log x minus a ninth x cubed. Okay, so we shall add 6i and 6j to our list of questions.